In the previous video, we proved one half of Artin's theorem. So recall the statement says if K is a field and if gamma is a finite subgroup of the group of field automorphisms of K, then K over the fixed field K gamma it's a finite extension of degree equal to the cardinality of gamma. And we proved the inequality which showed that the cardinality of gamma is less than or equal to the degree of the extension K gamma. What we'll do this time is to prove the other half. So I now claim that the reverse inequality holds. In other words, that the cardinality of gamma is greater than or equal to the degree of the extension. F, remember, is the fixed field of gamma. Okay, and how are we going to prove this? We will prove the following. We will prove that any set of linearly independent elements, any set of linearly independent elements of K thought of as a vector space over F. Okay, so maybe to emphasize the field F, I'll say F linearly independent elements. So I think of it as K as a vector space over F, and if I show that any set of linearly independent elements has cardinality at most the cardinality of gamma. Okay, now if you show this, then you're done, because this would imply two things. Number one, that K over F is a finite extension, because otherwise there would be infinitely many linearly independent elements possible. Secondly, the dimension of this vector space is at most the cardinality of gamma, because you just take a basis of this vector space, that's a set of linearly independent elements, and that can have cardinality at most gamma. Okay, so let's try and prove this statement. So let's begin with a set of, let alpha 1 through alpha m be a set of linearly independent elements. So again, let me say F linearly independent elements of the vector space K thought of as a vector space over F. Okay, and of course I will assume M is at least 1 here. So some finitely number of them. Okay. Now let's show that. So maybe I should say any finite set. Okay. Now what do we know? Since this is linearly independent, from this we can get many other linearly independent sets as follows. Since each sigma in gamma fixes, so you pick an element sigma in gamma, since it fixes the field F pointwise, right? In other words, since it's a fixed field, sigma acting on an element of F gives you back that same element. We conclude the following, that the collection sigma alpha 1, you just apply sigma to all these earlier fellows, alpha m, this is also F linearly independent, is also an F linearly independent. So I'll just use Li for linearly, it's an F linearly independent subset of K. Okay, so we have manufactured in some sense many linearly independent subsets, starting with the first one, and now comes the sort of important step, non-obvious step. Let's define maps as follows. So we have a bunch of linearly independent sets, and we are going to define maps from Km to K as follows. So I will call this map as psi, but this map will also depend on the sigma as follows. So given a m tuple beta I of numbers in K, I will map this to the corresponding linear combination of the linearly independent set sigma alpha I. So remember, sigma alpha is linearly independent, and I just map the collection beta i's to the corresponding linear combination. Okay, so observe there is therefore this is maps one for each element of gamma. Okay. Now, what are the key properties of these maps? Well, the first property, the sigma alpha I are linearly independent, thought of as over the base field F. So the linear independence tells you the following. If you look at the kernel of this map, okay, so if I ask what's the kernel of this map, in other words, what's the collection of m tuples which maps to 0, I equals 1 to m. Well, in general there will probably be many of these, but if we take this to be the kernel, then observe the following. The kernel of sigma psi sigma does not intersect f power m. In other words, if all the beta i's come from f, then this linear combination can never be 0, okay, unless all the beta i's are 0 themselves. This is exactly linear independence. So by the f linear independence of the sigma alpha. Okay, so the beta i's can't all simultaneously come from the base field f. Okay, property 2, observe that psi sigma is actually a k linear map. So what sort of map is this? You can think of it. So now the k to the n and k, if I think of them as vector spaces over k, okay, then psi sigma is just a linear transformation of these k vector spaces. Okay, so this is k linear. In other words, if I add two guys, it will become the sum. So if I take beta I plus the tuple beta I dash, which means component wise addition, then it will just give me psi on beta I plus psi sigma beta I dash. Okay, and I mean that's more or less obvious, because you will substitute in place of beta I, you will have to substitute beta I plus beta I dash, and so it will split up into two pieces. And similarly, if I replace beta I by a multiple of beta I, in fact a multiple coming from k, a scalar multiple, so that's the second property. If I apply psi sigma to lambda times the beta i's. So let me just verify this. Psi sigma, this is just the m tuple lambda beta I by definition, and this is just lambda beta I times sigma alpha I. This is I goes from 1 to n. Okay, so observe this product is taken in f. Lambda and beta I are in f, so lambda beta I is another element of f. Sigma alpha is of course an element of f. And so now by the associativity of the multiplication of the field, I can just pull the lambda out. Okay, so it will give me beta I sigma alpha. Okay, and so this is true in fact for all lambdas coming from the field k. So this map is a k linear map. It satisfies additivity and scalar multiplication. It respects both operations. Okay, now that's the second property. So what do we know therefore about the kernel of the map? So by the way, here's one property we know about the kernel. But now because it's a k linear map from k power m to k, so this is what you would call a linear functional on the vector space Km, the kernel is a subspace, right? It's a subspace of Km. So again, just to emphasize that I'm talking about vector spaces over the field K, I'll say it's a K subspace of Km. Okay, so here there are two fields K and F in play, and sometimes you may think of something as a vector space over K, sometimes over F. So just to ensure we are not getting ourselves mixed up, I'm just emphasizing the K or the F. Okay, so the kernel is a K subspace. So that's the second property. This K subspace is interesting. It does not intersect F power m, okay, where F is the base field. Okay, and what's the third property? And this is somehow the most important, one of the most important properties of these maps. And this really uses the fact that gamma is a group. So observe that the earlier half of Artin's theorem did not really use the fact that gamma is a group of automorphisms. The group structure was not used, but now we are going to use it. Okay, so here's the observation. So suppose I pick an m tuple beta I from 1 to m, which is in the kernel of sigma psi sigma. then what does that mean? It just says that the sum beta I sigma alpha is 0. Now what I can do is I can apply an element of gamma, okay, an automorphism. Okay, remember gamma is a subset of the automorphism group of the field K. So I will apply tau to this equation. So what does that mean? It will give me summation. So it's tau acting on this sum is 0. But tau being an automorphism, this can be written as the sum of tau of beta I into tau of sigma of alpha I. Okay, so I've used the fact that tau respects both addition and multiplication, and now observe tau sigma is just another element of gamma. Okay, so what does that mean? It says that if I look at these numbers tau beta i's, so maybe I'll give them a different name now, beta I dashes if you wish, then it says that, so this says that these beta I dashes, this new M tuple is actually also in the kernel of psi, but not of psi sigma, but psi of tau sigma. Okay, that's exactly what this equation implies. So here's the conclusion. If beta I belongs to the kernel of psi sigma, then tau beta I, so let me just again call beta I dashes as tau beta i's. So if I apply tau to each component, then that resulting M tuple is in the kernel of psi of tau sigma. Okay, and this is true for all sigma tau coming from gamma. So this is the third and important property that we need. Okay, now what does this imply? This third property especially, it says the following. If we take the intersection of all these kernels, so let W denote the intersection of all the kernels. Okay, what is this? Some subset of K power M. Then this intersection has the following property. So just look at what this says. If you have something in one kernel and you apply an element tau to it, it lies in a different kernel, right, of one of the other psi's. But if something comes from the intersection of all the psi's, then if you apply tau to it, the answer is again in the intersection of all the taus, all the psi's. Okay, so if W is defined like this, then the conclusion is the following. W is invariant under gamma. Okay, this means the following. Then if I apply tau to W, the answer is again in W. So if beta I belongs to W, and so does tau beta I. Okay, so this invariance under the action of gamma. So I should say this is for all tau in gamma. So we are going to use this invariance under the action of gamma. So this is one property again. So this is the first property of W, and of course the other properties come from the previous statements, which is that W is of course an intersection of subspaces. So it's a subspace. It's a subspace of K power M, and in fact every one of the psi's itself does not intersect F power M. So in particular W doesn't intersect F power M. Okay, so these are the three important properties of W. Okay, now what does this give us? Well, I claim that you really can't find a W satisfying these properties. Claim is the only possibility for W is just the zero subspace. Okay, these three properties are just too strong. Okay, so proof, let's quickly prove this. So suppose there exists a non-zero element. So if there exists beta I 1 to M in W with which is non-zero with some beta I, say the ith term, maybe we should call it beta j, with some non-zero element with beta j not 0 for some j between 1 and m. Okay, so it's a non-zero element of W. Then we'll get a contradiction. So observe that since W is a subspace, K subspace, right, so maybe I'll call this M tuple as beta. Okay, since W is a K subspace, meaning it's closed under scalar multiplication by K, what you can do is the following. You can scale this element beta. Okay, we can scale beta by various scalars, by elements of K. Right? In other words, you can take beta and multiply it by various C's. So in other words, replace beta by a scalar multiple of beta, where the scalar comes from the field K. Okay, and when you scale beta, and we can scale beta by elements of K, and so maybe I should say by rescaling beta. Okay, we may assume that this non-zero element beta j, we may assume beta j is any given element of my, it's an element beta j is lambda, where lambda is some fixed, let me fix some where lambda belong to K is some fixed element. Okay, in other words, I can, by rescaling, I can ensure beta j is anything, any element I want, okay, any element of K. Okay, so I am going to fix lambda and I will rescale beta so that beta j equals the value lambda. Okay, now what's the point of this? So now let's apply the three properties of tau. So observe, first I apply three properties of W. So now let's look at this property here. We know that if you apply tau to beta I, this answer is W. So we know this was property 1 that I mentioned of W, okay, for all tau in gamma. Okay, now here's a standard sort of trick that one uses to construct elements which are invariant under actions of finite groups. So let's consider the sum of all these tau beta i's. Okay, so let me call this new element as zeta. Maybe let zeta denote the sum of all these tau betas. Tau belongs to gamma. Okay, so this m tuple I am calling as tau beta. So this is now an m tuple. When I write tau beta, I really mean an m tuple here. So maybe I'll put a underscore into the beta to say it's like a vector. Okay, so look at this new element. This is an element of K power m. Okay, and what more do I know about it? The key property is that this is invariant under the action of sigma. So consider there is some zeta. Not only is it in K power m, it's actually in W. Okay, why? Because each of the tau betas is in W. So their sum is in W. Now the important property is, if I apply any element sigma to zeta, where sigma is, so let sigma be an element of the group gamma. If you apply sigma to zeta, then the answer is just sigma tau beta. Okay, but when tau runs over gamma, sigma tau also runs over gamma, possibly in a different order. So this is actually the same as zeta again. This is just the same sum, except that the terms may appear in some other order. Okay, so this is the key property. So sigma zeta is actually equal to zeta for all elements sigma and gamma. So what does that mean? If I write zeta as say zeta I equals 1 to m, this m tuple, then it means if I apply sigma to these components, so then sigma zeta I, so the m tuple sigma zeta I coincides with zeta I, means that each of the components, when I apply sigma to zeta I get zeta I for all I equal to 1 to m. This is true for all sigma and gamma. Okay, so now we stare at this last equation here. It says that the zeta i's that I have, they are fixed by every element of gamma. Okay, they are elements of K, but they are fixed by every element of gamma. In other words, the zeta i's are all in the fixed field of gamma. Okay, this is true for all I equals 1 to m, but the fixed field is exactly what we are calling F. Okay, So to summarize what this trick finally does, we have one element beta in W. Okay, now we know that W is invariant under applying elements of gamma. So you apply all the elements of gamma, the taus, and you get many vectors, tau betas. Now when you add those vectors up, the final answer is definitely invariant under, it's fixed by the action of gamma, okay, because you have taken a sum. Now this implies that the zeta i's are all in F. So what does that mean? We have constructed, so zeta therefore, which is the tuple of zeta i's, is an element of F power m, and remember zeta was an element of W to begin with, and now recall that was the second property which said W has no elements whose components are all in F. Okay, so we have constructed one such element, which means that the zeta must actually be the 0. So zeta I had better be 0 for all I equals to n. Okay, so what does this mean? This says in particular, let's just apply it to the jth component. So remember, we know that at least one component beta j was not 0. So take I to be the jth component, where beta j was the given lambda that we fixed. So then what is zeta j by definition? It is summation tau beta j, tau ranging over gamma. This is what we call summation tau lambda, right? Lambda was the value of beta j. Gamma, this is 0. Okay, so what does this mean? This says that summation tau of lambda is 0. Tau belongs to gamma. Okay, but now is the interesting thing. Remember, the lambda was arbitrary to begin with. Okay, so we could have chosen any element lambda of the field K, and why was that? Because beta j was non-zero to begin with, so you could scale and change its value to any element of K. Okay, but lambda is arbitrary, but lambda in K was arbitrary to begin with. So this implies that summation tau, when evaluated on lambda is 0 for all lambda in the field K, tau coming from gamma. This means that if you think of these as just maps from lambda to K, okay, so this identity is when I'm thinking of all the taus as being maps from K to K. Okay, it's the linear combination of the taus. Just the sum of the taus is just the 0 map. That's what this means. Okay, but recall, we have proved linear independence of characters, right? The taus after all are characters, and of the multiplicative group of the field and so on. So remember, one of our corollaries of the linear independence of characters said that the automorphism group of a field is always a linearly independent subset of maps Kk. Okay, but recall that gamma is in fact K linearly independent. Okay, but then this thing here contradicts that. This is a contradiction. But summation tau is 0 means they are linearly dependent. Means gamma is linearly dependent, right? This is a linear dependence relation among the elements of, and that's your contradiction. Okay, so this proves the second half of Artin's theorem. So what we have really shown is that the there's still one little thing that we need to do. We are almost there. So what does this prove? So we have only proved that W is 0. So therefore our conclusion is that W is 0. Okay, but that's not what we wanted to prove. The starting, so recall at this point, let's just remember what did we want to prove. We started out with, so recall, want alpha 1 through alpha m was our original linearly independent subset. This was the F linearly independent subset of K. We wanted to show that this number m is at most the cardinality of gamma. This is what we wanted to prove. Okay. Now along the way we have sort of constructed a certain subspace W and shown that that subspace W is 0. Okay. So how does this subspace being 0 tell us that M can be at most the cardinality of gamma? That's the last step that we need to complete. So now consider the following map. So I had, remember, from Km to K I had a map which I called psi sigma, but now I'm going to stitch all those maps together. So I'm going to define from Km to mod gamma copies of K. So this I will write as, so I don't know, let's just keep it like this for the moment. So what is psi? It's the following. I take an element beta and I map it to, in the first component I'll map it to psi sigma 1 of beta, psi sigma 2 of beta, and so on. Psi sigma, what name shall we give? N, maybe sigma n of beta, where gamma is the set sigma 1, sigma 2, sigma n. Okay, so I had a map psi sigma 1 for each element of my group gamma. Now I'm just stitching together all those maps, forming one single map from k power m to how many copies of k? This is k power n, where n is the cardinality of gamma. Okay, so I have a map, and remember that's starting to look like what we want to show that m is at most n. If we show that this map is injective, for example, it will prove that the domain has to have dimensions smaller than the range. Okay, and that's what we'll show. Okay, now observe psi is, so we are more or less done. Psi is a k linear map between these two k vector spaces. What's the kernel of psi? So this is obvious, the k linearity, because each component is k linear, and the kernel of psi is, well, all those betas which map to 0, 0, 0, 0 and so on. That just means that beta should live in the kernel of each of the sigma i's. Okay, but remember that's exactly what we called, well, that's kernel sigma psi belongs to gamma, we rewrite it like that. That's exactly the subspace W. It's the intersection of all these kernels of the psi sigmas. Okay, and now where does that leave us? We just showed that W is 0, right? That was the whole point of the proof. And so it means that this map psi is actually an injective map. Its kernel is 0, therefore psi is injective. Okay, or a one-to-one map. Now an injective map between two k vector spaces means that the domain vector space must have dimension that's at most the dimension of the codomain, okay, or the range. So in this case M can be at most the cardinality of the mod gamma, which is what we called n on the left hand side. So that now completes. So this completes the proof of Artin's theorem. Okay, so next time we look at some consequences of this theorem.